So this video is basically a case study related to horizontal flow boiling. So this is the problem we're going to solve. You can see that we have a 1 centimeter diameter tube, and in the tube is flowing R454A, which is a mixture. So we have to remember that mixtures are going to have a temperature glide as it boils. So this mixture enters the tube as saturated liquid with this mass flux of 100 kilogram per meter squared second. And as it flows through the tube, it's being heated, so it's boiling. It's being heated by this flow of air across the tube. The air is at 100 degrees Celsius and it's flowing at 25 meters per second. And we're going to neglect any pressure drop along the tube, so the pressure everywhere will be constant. But what we'd like to look at is what is the temperature of the fluid, so that temperature glide as it evaporates, and the quality, and then also the tube surface temperature and the heat flux as a function of position along the tube. And basically, how long does this tube need to be to almost completely boil the R454A? So, if I wanted to come out at 90% or 95% quality, how long do I need to have this tube? So that's the problem, and I'll give you some time to go work on it. And we're going to, again, use the heat transfer library, and in particular the boiling and condensation part of that library, in order to solve this problem. Alright, so my strategy is going to be here to first of all set up my program so that if I specify a quality, any quality from 0 to 1, my program will call the right flow boiling correlation and the right external flow correlation and figure out at that quality, what is the heat transfer coefficient on the inside of the tube and the outside of the tube, and from that, what's the heat flux, and from that I can figure out what is the rate at which the quality is changing. And of course, once I have that, it's just a matter of integrating along the tube. And I can either integrate along the tube myself numerically, or I could use the integral command in ease. So let's go ahead and try to get that going. So I'm going to start by setting the unit system. I'll use SI, mass, Celsius, kilopascal, and joules. And then I'm going to put in all of the inputs from the problem statement, and those include the inlet temperature. What else? The inlet quality is 0. It's saturated liquid. The fluid is this mixture, so R454A. The pressure is given by the inlet quality and temperature. Those two things together will give me the pressure. We got to remember this is a mixture, right? So I can't use PSAT, but I can use the function pressure with fluid $ at x equals x in and t equals t in. And that pressure ends up being a little more than a megapascal, and this pressure will be constant in the tube. That's our assumption, is that there's no pressure loss. The diameter is 1 centimeter to 0.01 meter. The mass flux is 100 kilogram per meter squared second, and then I know the air temperature and velocity. So this is 100 Celsius, and the velocity is 25 meters per second. What else? I don't know the length of the tube. I'm just going to set it to some very large value for now, and we'll have to cut off our integration when we, completely boil the tube. We'll talk a little bit more about that in a little bit. And now I'm going to go ahead and set a value of quality. So let's set it equal to, I don't know, initially x in, and I'll make sure that for any given value of quality, like I said, I can figure out the heat flux, right? So the first thing I have to remember is that at any given value of quality, the temperature will no longer be Tn. It'll be whatever temperature is dictated by this pressure and this quality. So T, this is the temperature of the fluid, is temperature of the fluid at x equals x and P equals P. So because I set x equal to x in, I should be getting a T of 20 degrees Celsius. But as I march along the tube, that's not going to be the case anymore. Alright, so the next thing I need to do maybe is go look at what do these flow boiling functions look like. So I'll go to function information and heat transfer. We're not doing pool boiling, we're doing flow boiling. Turns out there's a few different horizontal cases. So the Shaw one is horizontal, Chen is vertical. I actually think one of these Hamilton is either horizontal or vertical. So we could probably pick between the Shaw or the Hamilton. Maybe we should do both just to see how different they are. But at least initially, let's put the Shaw correlation in there. So you see the Shaw correlation requires the fluid, the temperature, right? So this is just T of the fluid, the mass flux, the diameter, the quality, and then the heat flux, right, which I don't know. And this can either be horizontal or vertical. We're going to do horizontal because it's a horizontal tube. And it gives me back the heat transfer coefficient associated with the flow boiling and the wall temperature. So what I'm going to do is set a heat flux to something, I don't know, reasonable. It's probably a little low. And I'll have to come back and adjust this heat flux so that it's consistent with the air temperature and the resistances that separate the air temperature and the fluid temperature. But right now, I can use this heat flux and I can solve. And for this heat flux, I find out that here's the heat transfer coefficient and here's the wall temperature. Okay. Next thing to do, I think, is go ahead and figure out the heat transfer coefficient on the outside of the tube. So sticking with the heat transfer library, but now convection, and in particular external. We can either do dimensional or non-dimensional. It's a heck of a lot easier to use dimensional. So this is flow across a sphere. I want flow across a tube. So let's paste that guy in there. It needs fluid, so this fluid is now air. It needs the free stream temperature. It needs the wall temperature. So this is the same T sub wall that we calculated here. The pressure here is atmospheric pressure. This is the velocity, called it U infinity, and the diameter. And it gives me back the drag force per length, which I don't care about. The outside heat transfer coefficient, which I want. I don't care about the drag coefficient, or the Nusselt number, or the Reynolds number. So if I solve now, calculate solve, I should see that I have both the internal and the external heat transfer coefficient, which is what I wanted. So this heat flux is not consistent with these two temperatures, the fluid temperature and T infinity, and these two heat transfer coefficients. So the next thing I have to do is make that consistent, right? I got to iterate on this heat flux, and that iteration is probably going to require that I have a pretty good guess value. So I'm going to go ahead and use the var_info command up here, $var_info, and the variable is heat flux, and I'm going to put in a guess of, I don't know, let's put in a guess of 1,000, and it's going to have a lower limit of 0, and I don't really know what the upper limit is, but this is going to make sure that my iteration is hopefully pretty well behaved, right? And so now down here, I can go ahead and calculate the heat flux that is consistent with these temperatures and these heat transfer coefficients, right? So the heat flux is equal to T infinity minus T, and the resistance, if we're not including the conduction resistance of the tube, is just 1 over H out plus 1 over H in. And of course now I've overspecified my problem, so I probably want to comment this out. And hopefully now if I solve, it'll iterate and find that, yeah, the heat flux is actually right there, right? And the wall temperature is nicely between 20 and 100. It's 46.55. So hopefully that makes sense. The last thing I need then is to figure out from an energy balance, how quickly then is my quality changing as I move along the tube. So let's think about that for a second. So here's a differential control volume. You can see it's differentially small in the direction of the tube, but extends all the way across the cross section. The energy balance then is that the mass flow rate times the enthalpy entering on the left has to be equal to the mass flow rate times the enthalpy leaving on the right, which I've expanded here using a Taylor series expansion, taking advantage of the fact that ds is going to go to 0. And then also you have the heat flux entering at the perimeter of the tube. So these three terms have to be equal, which is what we've done up here. And then you can simplify this by subtracting the mass flow rate times the enthalpy from each side, and then also getting rid of the ds on each side. And that leaves this equation, which just says that the rate at which the total enthalpy flow rate is changing is driven by the heat flux. Let's pull the mass flow rate out of the derivative because it's constant and express it in terms of the mass flux. So it's the mass flux times the cross-sectional area of the tube here. And then we will recognize that the enthalpy change here is the latent heat of vaporization, HFG, multiplied by the quality change, right? So that gives us this equation here, which I can solve for dx ds, right? The rate at which the quality is changing as we move along the tube in the flow direction. So that's what I've done here, and then this last step is just simplifying this by, I guess, dividing the top and the bottom by pi d. So this is my energy equation that I'm going to implement in ease. Alright, so let's first of all get the latent heat of vaporization. So that would be what? Enthalpy underscore vaporization of fluid dollar at, we got to use P, right, because we're doing this vaporization process at a constant pressure. So like that. And then we'll program that energy equation. So this is dx ds is equal to 4 times the heat flux that I calculated, divided by, let's see, I think it's d times g times hfg. So if I solve now, I should get dx ds, which is, what would that be, 1 over meters, I think, right? And that seems to work out pretty good. Okay, so let's go back here and actually do the integration. So I'll update my guess values. I'll get rid of the integration variable here, and instead I will use the integral command. So x is equal to xn plus the integral of what? I guess it's dx ds with respect to s from 0 to here. We'll go to the end of the tube, although I suspect we'll have troubles after we vaporize everything, because a lot of the code here is going to break down once we get out of the two-phase region, but let's put that in there. And then we'll do dollar integral table. So the integration variable is s, and we want to keep track of some things like the quality, maybe the wall temperature, maybe the heat flux. What else? Maybe the heat transfer coefficient on the inside of the tube is kind of interesting, and then certainly the fluid temperature. So if I run now, let's see, calculate, solve. You see it runs for a while, and then it gets out of the two-phase region and sort of gets stuck. So let's look at the integral table. So Windows, integral tables, and you can see that it's working pretty well. Quality goes up, and then somewhere, so quality goes up, and then right about here at 3.8 meters, you can see that we have a problem where we come out of the two-phase region. So this is a really good place to introduce the integral stop directive, which is basically just asking you to stop the integration when some condition is met. And the way the integral stop directive works is you say integral stop, and you give it the integration variable so it knows which integral you're talking about. So the integration variable here is s, and you give it the condition. So let's stop when x is greater than 0.90 or 95 or something like that. So basically we're going to stop as soon as the quality goes above 0.90. So hopefully this works. Let's try to run it. So calculate, solve. You can see it hit the condition. It's asking, do you really want to stop? You'll say yes. And if I go look at the integral table, it's fully filled out, and you can see that when it went through this one step here, 0.8781 to 0.9118, it decided it was done, and it took about 3.5 meters of tube to do that. So let's go ahead, and I guess we have one unit error, which is my integration variable is in meters, and we will make the plot that was requested. So here, what did they want? They wanted as a function of tube, the quality as a function of tube length. So what does that look like? It sort of just goes up, not quite linearly. Maybe more interesting is as a function of tube length, you could get the temperature. So that's kind of interesting because it should show the glide. So sure enough, even though we're evaporating at constant pressure, you can see the temperature changes. And then maybe really interesting is the heat flux and the wall temperature. So let's do, I guess, the wall temperature, and then maybe on the other axis. So let's overlay, let's not do that. Let's overlay on this plot the heat flux, but we'll put it on the secondary scale. So it looks like that. So that's kind of interesting. It shows the high heat flux that you get when you're in the annular region, and then it drops off as you start to dry out. You can probably see this even more clearly if we did the heat transfer coefficient. Let's do that. So yeah, you can see kind of the funkiness of the heat transfer coefficient in the two-phase region. So hopefully that makes sense. You know, there's all kinds of things you can do with this. You could, for example, instead of using the Shaw correlation, you could use the Hamilton correlation. It would change things a little bit. You could change the fluid. You could change all kinds of things. But you can kind of see the power of this technique, showing you kind of what's going on in this actually relatively complicated problem.